For the first computer science lesson after summer holidays in 2002, 23 years ago, I had set the students the task of moving balls, walked through the rows and came to Ulf. He said, the table, the door. And he said to me, Doc H, that's what they called me, Doc H, this solution in the book is not completely object-oriented. I said, that is impossible. This assignment comes from the most renowned computer science educator we have in Lower Saxony. It was Eckhart. But he was right. Ulf was right, not Eckhart. Today, Ulf has a doctorate in computer science and is designing and building windmills. Why couldn't I see that there were still remnants of older paradigms? I am influenced by the first programming languages I learned myself, UCSD Pascal, Turbo Pascal, and Delphi. And I tend to transfer concepts I learned with these languages to new tasks. These include, for example, strict typing, the measure to save memory space, in-place procedures, also for lack of memory, avoiding dynamic data structures. And many computer scientists of my generation feel the same way as I do, but rewrite the textbooks, the manuals, the internet sites. And that's why we find such outdated solutions in many books and in the internet today. We make programming unnecessarily complicated. 3 years ago, I read a new script about programming with Snap. And I stumbled across the finite state machine, an acceptor. And I thought to myself, none of my students would program such an acceptor in such a complicated way anymore. Why is it still in the script? Students who have grown up without our baggage have it easier in this respect. In spring 2011, I read the famous article, Why Java, from Jens and Eckhart and Kerstin. And in autumn, the same year, I started teaching BYOB. And I began to hear more and more often, Doc H, there is a much easier way to do that. And I started to write these things down. We collected the ideas and passed them on to the next course and to the next course for the next 12 or 13 years. I used two types of sources for this workshop. Since the early 2000s, I have been using learning management systems where the students had to upload their solutions. So this has grown into an extensive collection of data. So I can say, how did we sorting in 2011, 13, 14, all the years since then. And for this workshop, I reviewed my worksheets and the corresponding student solutions since 2011 and asked myself, why did we start using new solutions or improving existing ones? The old programs, I will show you, that we discarded at a certain point are marked in gray. The others are colorful. The others, I will show you only the second phase. Most of these were made again when we switched to functional programming. So we have three solutions. The original one, textbooks of 2000, 2010, then the improved one, and then the third one with functional programming. The second type of source are evaluations I wrote after correcting each central Abitur high school exam. I asked myself, what mistakes did the students make? Are there mistakes that occur more frequently and reveal weaknesses in my teaching? It gives me clues as to where I can change my teaching. Two more notes. You will see that the headers of the blocks always consist of a name written together in one word, and then a list of parameters in parentheses, rather than alternating between names and parameters as proposed yesterday. This is simply because the notation I used is prescribed by the German curriculum. So I cannot use another one in my classroom. And local variables always begin with a lowercase as specified by the curriculum, while I begin global variables with a capital letter for better differentiation. So these are our outdated programming has to be strict typing to save memory. It prevents for in-place algorithms, avoid dynamic data structures. I have a book, Delphi 7, 1,200 pages. Lists start on page 712, and it's less than 2% of the whole book is about lists. So lists, which programmer would read till page 700? So lists are completely out for programming, no chance. Avoid linked lists. We prefer numerous global variables, and we avoid parameter passing. Is it pronounced right? Parameter? Yeah. Parameter. So we take the examples. No, there's another one. This one. So just make a note. That was insertion sort as we did it in 2011. You see, we take a command. We take a global variable data, and we have two indices sorted. It's going upwards, and count variables E is going downwards. And then we place this, and we have this lot of replacements, and it's rather complicated. The first step was to make it a reporter which gets the data you want to use. And the second important step is, that was not me, it was one of the pupils said, it's much easier if we take a second list. And instead of having two counting variables, we only have one, and we take the data of the old list of fund data and put it into a new one and the result. And when we report result. And so instead of two count variables, we have only one. It's much easier for the students. For us, it's no problem. We can use these kind of problems. But for the students, it's much easier. So that was insertion sort, the same. We did the same with selection sort. The old version was in command with global variables, parameter, and then we have to go through these indices and to this replacement. We have here only one replacement, one swap, because we only take the first the smallest element of the unsorted and put it on the right place. And we did the same. We made a reporter, and we took a second list, and it was half the program code and much easier to learn. The result of these many swap operations in the when you give the task implement a sorting algorithm, at least 4/5 of all students use the non-optimized bubble sort. We have two count sorts, and these both go upwards, and so that was a level of complexity they could master with. So they preferred bubble sort. This changed when we use this. This way is much more easier than a bubble sort. So that was the third, and then we came merge sort. And merge sort was done as a command 2, but we had to get two parameters. We had a global variable data. No, it's not here, but it's the data. And then we have two separate lists, left list and right list, also global parameters, a result list, global parameter, and then we had to work on the data and from till is which part of data we are just working on. So we get the middle, and then the lower part gets into gives the recursion, which is merge sort, and the upper part too, and then when we have these sorted parts, we fill the partial lists and merge these partial lists and then apply the values. And have a look. The merge sort is standard merge sort. Wieso will das nicht? Na, dann nicht, dann machen wir ihn so. Merge. Da ist es. Standard merge sort, repeat until right list is empty. This is the global variables, or left is empty. We compare the two first elements and put the right one into our results list and delete the other one. And then we make some really stuff that's really not needed, but we come to this later. So this is nothing special about this. And then we have to merge these lists, and we have the other was we had to fill these lists, and then we had to apply the values, which only takes the values from the results list, starting with position, and writes them into the data. That was our first solution. For the revision, we first moved the merge out of the block, because we discovered merge is not only restricted to merge sort, but is needed in various other contexts too. So we decided it makes sense that we have an operation merge, which operates with lists that with every list we needed it, and we can merge. So that we made two parameters, data 1 and data 2. And this was the first one. This is the same as before. And then one of our students said, but when we are ready with this loop, with this repeat loop, one of the, either data 1 is empty or data 2 is empty. So instead of taking two additional loops, repeat until 1 is empty and repeat until 2 is empty, we just can put these three lists together. One of them is empty, and so there's no problem. It's still sorted. So this idea saved about half of the source code. So, and the new merge sort block uses, of course, merge, and I think it's very, so. We have, of course, we have data as parameter. We have left part and right part and one counting variable. And we have now recursive structure. So we have a base case. What is a base case in merge sort? We have partial lists of length 1. This is the smallest we can get. And in fact, so if we have a list of length 1, it's already sorted by definition. So that's our base case. So we report this. And then we have to fill these, the left part and the right part. We did this afterwards. We did this with higher order functions. And then the algorithm is just this: merge sorts right part, merge sorts the left part, and then merge these two parts together. And this was much clearer for the students than the older one. We said, oh, that's the left merge sort. That this is an easy one, which was not the case before, with all these indices and then this merge sort. So we found other solutions with high order functions. I have not just listed them here. The third problem was simulating multidimensional data structures. So we all knew, we grew up believing that a memory is a linear data structure, and that multidimensional data structures can realistically only be simulated within a one-dimensional array. So if we use a matrix or a table, 1, 2, 3, 4, then we have the first line. We can write the first line, 1, 2, 3. The second line, 4, 5, 6. And then we need the width and the height, the number of columns and the number of lines, this says, for getting it back. So we must differentiate between a 2, 3 matrix and a 3, 2 matrix, for example. And so this need, we do tables in this way. We need additional get and set operations. Now, the other one, get and set. So the area, the indices at the get item, and then I have to these to m and n. I can get from the first and second element, and then I have and have to make a reason. This is the get and set operation with a mathematical index. For the mathematicians, we start in the left corner with 1. So the first element above is 0. It's not 0, it's the first column and the first row, 1, 1. In computer science, it's not 1, 1, it's 0, 0. So we should have transformed the mathematical coordinates into computer science program and then transferred it back into physical coordinates, and they said this was too complicated for us. So we left this out. It's not really correctly. We use a mathematical definition of a matrix and not computer science one. But it would be only more complicated. So we left this out. We said, it's mind-blowing. We did not know. And in the same way, we need a second get operation, set operation. So this is now it's in command, and we have the same formula checking is it within the limits of the matrix, and let's say it's out of limits. And this was not much easy, not very easy. And I looked it up. At one point, I actually taught simultaneously 3 different ways of implemented a matrix. This one, linked lists, and a third possibility that was only for simple tables whose elements consisted of one element, one character, a list of character strings. Yes, like this one. Now, like this one. So we had this would be a 3 100 table. So we taught 3 different types for nothing. We should have stayed with linked lists, but it would have been much easier. We would forget all these get and set items and so on. This was the second, the 2-dimensional and 3-dimensional data structures. Then the finite state machines, I mentioned the example, it's not from my courses, but from the SMAC Berkeley website. There is an acceptor which should check an email address. So the first function we have A1 or A, and then there may be more of them, and then comes at, and then B, maybe more than dot, and DE for Germany. And this is email checker. And the implementation I found in the internet was this one. The predicate goes through the letters of the address and takes each letter and then goes through a lot of nested. I think it's mostly 8 if then else, if then else. I think at this point we have 1, 2, 3, 4, 5, 6, 7, 8 nested loops. And it's almost exactly the same we did in Pascal, only then we had used the case loop and got only 2 nested loops. But apart from this change from if then else or case, it's the same solution. So, and I was not, I had the template in front of me, and I was not able to program it in the first try. I had two errors in it. It's very complicated. And it fits only for this one machine. The slightest change in the machine, in the email checker, would mean a total different program. So this was how I learned to do exceptionals. Then my students came and said, oh, nonsense. We know that a finite state machine can be described through the transition function. And we have the inputs and we have the states. And we take the actual state, maybe Q2, and we take the actual input, and then we can only get the next state. So what's the problem? Why these complicated 8 nested loops? It's much easier. And they came up, not the first time try, but we improved the solution. They came up with the following solution. It's a little bit smaller. I think it's 1/10 of this original text. So what is this? We have already a for loop. We can get rid of these two chaos. We have a for loop. We go through the address. And then we look up the letter of the address is the input, and which input has it in the input alphabet. This gives us the row. And we look up the state in the set of states, which index, and this gives us a line. And then we get the state from row and from line and row, no, from row and line from the transition function. And then we report if the set of final states contains the state or not. Well, this solution was very elegant. I was very proud when we get it. But then one can say, but we still need a filter because we use as input device a keyboard. And there are a lot of keys on the keyboard which do not fit into our input, into our set of inputs. So we must have a filter and eliminate all signs, characters. For example, Z was not in the input, and what is not into, we only have .1 at ABCE, and all other characters are wrong. And then someone said, yes, but when we take the solution, and we check every input here. So every input we read, we had to check it. And we use the index of block. And if the letter we come across is not in the input alphabet, this block gives us 0. We don't have it in the alphabet, so it gets the index 0. So we can use this to implement the filter into this too. So we can get rid of the filter block. And then they came up with this one. We go through the letters, and if the index of the actual letter in the input alphabet is 0, then it's wrong. So we report false, and then the rest is as we just saw. And then our email checker, after some weeks of, I think it was the second course who finished this actually, not the first one, our email checker. So we have the input alphabets, we have the set of states, we have the transition function, we have the set of final states. In this case, it's only one element. We have the state, it's the starting state in this one. And we ask which input should be checked, and this is our email checker, one line. And if you have another finite state, you only have to make another input alphabet, set of states, transition function. So when the students got a finite state machine in the Abitur exam, said, oh, I know how to do this. No problem for me. I take just the exact solution we had in the course, and we just have to implement these the sets and the transition function. So the third kind of third sort of examples I would give you are symmetric cryptographic methods, which are is there a question or symmetric cryptographic methods, which are in the German curriculum too. So, and the first is Caesar. I think everyone starts with Caesar. So we have, as usual, a command, and we have plain text global variable and cryptotext global variable. Key is already local here. So we just have two global variables. Yes. And we read the key and take the number of the key and create the cryptotext, set our index, and then we check is this between A and Z, and then the normal rate, we add the Unicodes mod 20 mal. This must be a plus. This is just so apply. Mod 26, and then give the letter and add the letter to the cryptotext. It did not look very good, but okay, we applied, we took it. And then the first student came, and then in the year we did the same. So we needed two indices, one for the E and crypto index, one for the for our text, and the second one for the keyword. Because the keyword was here a list of numbers. The key list is a list of numbers. But we needed two indices and had to manage both. We had to manage the crypto index. Students didn't like this one, and we had to check our index. So this was how we did it. I think most of the books, textbooks, still do it this way. And then there are several problems with this. The first, both solutions avoid passing parameters, which is a central concept for computing. So they say, we do this later. We must, in every course at one point, we must use parameters, but we do this as late as possible. And the second, there are other problems. We are just doing symmetric crypto algorithms. And with symmetric crypto algorithms, it is often the case that you can use the algorithm for coding, for decoding too. I give you two examples. The first one was here, our new Caesar. Plain and key were now passed. This is the same the same. This is the only distinction between this. But we have not a cryptotext and blood. The cryptotext will be reported. This is the same. And then we have Vignere also with two indices. No, with two. No, with plain code and indices, key code. Ah, yeah, this is Corinna Ahlers. Corinna Ahlers was she was not even in the advanced level course, she was in the basic level course. She came up and said, if we just duplicate the key and repeat duplicating the key till the key becomes at least as long as our plain text, then we need only one counting variables. We don't need a separate one for the key. So we need only one variable. And so we have here only one counting variables and takes for the E letter of the key, which is now longer as the plain text, and the E letter of the plain, and do the same mess. It was genius. Why didn't we do it? Because it costs memory. So we need the double space of memory, double space of memory. But it's makes it much easier. That's the first problem. That was Corinna. And then when we go to decoding, we use our Caesar reporter for decoding. We must just have to calculate a new key, taking the Unicode of the old key, 91 was mod 26 plus 64, and gives us this letter. And then it works both ways for coding and decoding. Or the other example, we can use it in Vignere. For Vignere is nothing more than just a Caesar applied multiple times. So we use Corinna Ahlers' doubling of the key, and then we have Caesar. And when we make a command, we not only get those global variables, but we cut the students up from a very important erkenntnis, from important insights in what a symmetric cryptographic algorithm is and how it can be used. And it becomes now clear to us if we change this way. This was, see, the second problem is more serious. The solution without parameters needs some global variables. And the Caesar encryption often contains two queries. What's the plain text and what is the key? It's no problem for us because we are used to it and we know how to do it correctly. But the student is writing his Abitur, his exam paper, under time pressure and stress. And so he remembers, oh, we did this in course number 11, and then he writes code like this. I didn't want to put it on the homepage. It's so ghastly. He writes code like this. We have a reporter, plain and key. The first thing is what is the key? Sets the key to answer. What is the plain text? Sets the plain to answer. He's overwriting these parameters, in this case with a query, in some cases with a certain fixed number. And so all the use of parameters and the sense of parameters is just blown out of the wind, blown out of the window. We get these if we start with commands. So when I saw this this is not, I saw this in one of these exams, and I said, no. If the next student comes up, Caesar as a command, I said, no, this is not allowed. You will not know why I forbid this now. but it will be important for you later. You must get what does this mean? And what is this for? And this is a central concept for computer science. It's one of the most central. So that's the problem with these commands. The other problem, the more serious problem. So then we looked for a solution which would allow us to avoid the mod 26 command, the mod command, for the younger students. Yeah, so that, and we could do it with this additional case differentiations if it's greater than, and then so we wouldn't do it that. And then we took a look and said, how do we start the lesson? We start the lesson on cryptographics for the younger courses with the Caesar disk. You all know this. We have two alphabets. We can change one another, and we have here now the letter D is a key, and we can the plain text, and this is the crypto text, and we can everyone. And can't we do something like this? This is easy. The students understand this. They have worked with the Caesar disk, and can they program this one? Yes, the answer would be, the first answer would be, of course, no, because younger students cannot handle lists, and we should therefore avoid lists as much as possible in the computer science course. When we questioned this assumption and said we use the list as a basic type, basic data type in SNAP, then there's actually a very simple solution. We need one list with the alphabet. Das ist with Caesar, das Caesar disk. So we need one list with the alphabet. Then we need a second one, first with a copy of the alphabets. This is a very, very it's worth to discuss the importance of the id block. If you just take a copy block and it will try it to get no encryption, why not? And so we can, normally I do it without the id block, and then we get, oh, it doesn't function, well, this is a problem. We can look at these two lists, and then we say, we need a real copy of this. And so we have the id block now. So we have these blocks, the alphabets and this the alphabet, and now we have to draw. Nee, drehen heißt, draw, bitte? Turn. We have to turn. We have to turn the crypto alphabet. How do we do the crypto alphabet? We take the first item of the crypto and put it on the back side and delete it. Most preferably in this the first adding and then deleting. That's complicated. So, and now we have our alphabets and our crypto alphabet, and what we do now, we go through our text, each letter, and look what index of has our letter in the alphabet, and we take this and the letter in the crypto alphabet at this index, and that's all. And we do exactly what we do with a Caesar disk. We turn to get the right key, and then we can't. So when we finished this, we thought this would be just a simple solution for beginners. The real solution for real computer science nerd is, of course, mod 26. But then we discovered it is just the opposite is true. The mod 26 solution is a special case just for Caesar. And I don't know if there's another, maybe we can construct a crypto algorithm, which also uses some kind of things. But substitution using a table is a very fundamental idea of computer science. And we discovered this when we just took the next one. After Caesar, Vignere, and Scutari, we took permutation uses not shifted alphabets, but a completely mixed alphabets, permutated alphabets. And then we can do the same theory. And we don't know how much time. No, I think we have to can show you another Beispiel where we can use exactly this one. We have a table and we do transition. Modern crypto algorithm, large RSA, use also transition as one step. So what we thought was a simple solution for the younger students turned out to be a very important idea of solving problems. Yes, I think I have some time left. I have prepared one example. I take two. Save. When we went over this, we started using higher order functions. We did not try to switch to functional programming. We started just using higher order functions for certain tasks. Instead, we have those higher order functions available, so we don't need to change the programming language. As in other cases, we just can't use them. And for example, before Jens invented the it block, we used some higher order functions for making deep copies. We could do it element for element with 4 tubes. No, this was not very much, but there was a possibility to use it with higher order functions. So we use these higher order functions for certain purposes. And we started to build a collection which purpose can be done with higher order functions. And then we started more and more using these functions and going over to functional programming. And then one of my students came up with quicksort. So, quicksort, reporter. And quicksort is, okay, no, will er nicht? Why not? Ah, yeah, have it. So quicksort is one of the most difficult sorting algorithms we teach in school. And in 2 years ago, on the Infos 2023 in Würzburg, we had a discussion, and the whole room was quicksort is too complicated for pupils. They cannot reproduce it. You can give them a template and they can program it. Okay, but to reproduce it. So my students came up with this solution. They said quicksort is a recursive algorithm. So recursive algorithms need a base case. So we need an if-else. So what is a base case? Contrary to merge sort, in merge sort we have only one element lists. We don't have an empty list in merge sort. But in quicksort, we can have one element lists which are sorted, and we can have 0 element lists which are sorted. So the base case is the length of the data is smaller than 2. So if the is smaller, kleiner, nee, nicht smaller 2. So the length of data So if length of data is smaller 2, this means we have a 0, length 0 or length 1, then we can report data because the list is sorted. Otherwise, we have 3 different paths. We take one element, pivot element, and take all the elements which are smaller, use quicksort on them, and take all the elements that are larger. And so we have 3 elements, and we can put them together, and we have now with append. So the middle thing is the list. No. Yeah. And which contains the first element of data, which is we take the first element as our pivot element. You must put it into the list. If you just put it in as first element, it wouldn't function. It would get you. We have the append block expects not elements but lists as parameters. So, and now we take the first, or we keep items from data which are smaller than the first element. Keep items from data. No, data doesn't exist in this context. And we take a merge quicksort on them. No.
Don't grab it from the hat block itself.
Quicksort ist, must hier unten, nee, noch nicht, ist nicht. Da ist es, quicksort. Ah ja, I got it. So we take a quicksort and just duplicate it, and we take those which are larger, and now we have to put it. So I think there must be a problem. We can just look at it. We have the base case and report the list from 3 parts, quicksort, keep all these are smaller and keep these as larger and keep running may apply okay in data, and we can quicksort and data. And when he came up with the solution, I was very proud. I was very proud. He's doing computer science. He's now studying computer science. But I said, so we have solved this problem. So I want to show you one problem, because there is a tendency in the SNAP community to use very complicated forms of nested higher order functions. And I think it's not very, very suited for the classroom. So I have a demo. Yeah, this is a demo, but we must have something. So we did Playfair. And Playfair was really hard at the first. And so we tried, when we switched to functional program, we can make it easier. And this is how with the solution which we came up. The first we take keyword, and in this case it's my keyword, and so the y is key here, and so we write the keyword in our lists without the doubles, and then the rest of the alphabet follows. That's the first step. And then the second step is we just write every M is the first row and the first column, Y is the first row and the second column, K first row, third column, qui veut, then the second row is O, R, D, A, B, and so follows. And now we have the coordinates in the Playfair quadrat for each letter. The next step is taking all the combinations of the different letters, MM is missing here, and the coordinates. And then we take the coordinates and say, how? If we have MY, both are in the first line. So MY 1121 becomes, we must shift right, becomes 2131. And then we look up what is 2131 and came up with a transition table, which looks like this. So MY becomes YK, my keyword. M was the first letter, Y was the second one, K was the third one. So the first and the second letter becomes the second and the third letter. And we make this, and then we just take our bgrams and substitute them with the other ones. So, and we will just show you an example like how we not. So, become this demo. So, the first thing is we init the key. We need snapcon. Now, snapcon Heidelberg. So if we init the key, we get this snapcon Heidelberg. The E is missing, Heidelberg, but it's only yes, snapcon Heidelberg, and then the rest of the alphabet comes. So now we have to, and we have the coordinates already. Yes, init key gives the coordinates. So now we make all possible combinations. Now we got a problem because the elements were lists, and so we got one list and a second list. We can look it up. Na, wieso funktioniert da? This is S and 11, and this other one is. So we have a list with two lists. First element is a list, the second element is a list, and we have to put them together. So we do it this way. We map and append the first item of the value and the second item of the value. Those two lists will be appended, and then we get the second. So now we have snapcon. Yes, it's not my keyboard. It's the snapcon now. There's S and S and S and N. So we now know S and S is not allowed. In Playfair, you must use different letters. We have to filter those different letters. And we keep only those items where the first and the third value are not the same. So just take it back. Okay. We have 625 data sets. And now when we get this one added, we should get only 600. Yes. And S is missing now. So now we have to take the first and the third and combine it in the second and the fourth. So we take get a map and make a list containing the first and the third element, and then the third and the second element. And it does what it's meant to do. And now we need the columns of this. And we get it. And now we have to transform the coordinates and get the second one. The main advantage of using the pipe block is that we can get every step by step, and can look what is the outcome. When there are problems. For example, we had the problem, we have to, in Playfair, we have to replace S, the German as Z with double S. And so we had, we did it in this way, just looking in the air. No, let's save it. Playfair, no, it's a upcase Playfair. So, so we had the alphabet and the umlauts, the German, and we took the present. And then we replaced J with I. And then at this point, we took the index of the letters. We had elements with lists with one element and with one letter, elements with one letter, and elements with two letters. And so we had a problem. But when we went through it step by step, we saw the problem is, these Z and A give two letters. So we might inserted a join here and split again. And so now we are sure just at one element, each element contains only one letter. And for teaching at school, at least, this is invaluable. And the students learn how to debug systematic. When I say there's a problem with the problem, how to do it. And we can do it step by step and step by step. And look at the output, the outcome, the output. And then find the errors. So, conclusions. I think I have a few minutes left. In his Carlson award speech on Monday, Brian mentioned three fundamental thoughts in computer science: functional programming, recursion, and higher order functions. And as a teacher, for me, the question is, how can we prepare for these fundamental concepts in the beginner programming lessons? And I would like to make some proposals. How can we pave the way for our students to learn functional programming, recursion, and higher order functions? First, we must ask ourselves, can we reduce the number of global variables? Global variables seem to be a very easy way, but it's misleading. You got more problems. Can we reduce the number of count variables? To reducing the number of count variables means to reducing the complexity of the problem for the students. When do we introduce the basic concept of parameters? Early, in order to make our blocks flexible. As early as possible, we work with parameters. Second, the third one, do we use reporters instead of commands whenever possible? But if you work intensively with reporters, I didn't decide one day we will learn functional programming. No, we did program with reporters and we started using higher order functions. And then one day we said, oh, this is functional programming, what we are doing. This wasn't a conscious decision. It was a slow form. Do we introduce lists early on, followed by lists of lists? Linked lists are a powerful tool for student-friendly solutions. Remember the finite state machine. You can do it the old way, or you can do it the elegant way. And do we use reporters that perform operations on lists or tables and return lists or tables? This paves the way for functional programming. With MAP, we have a programming languages that allows us to use higher order functions as building blocks in our programs. So we told it, we collect such building blocks in our course and use them. And this collection itself was a very strong incentive for the students to invent new blocks, for their new solution would be included in the common collection. And nested higher order functions are very impressive. I know Jens likes them very much, but difficult for students to comprehend. So let alone to debug. So they will use the pipe block in class whenever possible. We went through all our programs with functional programming and said, no, just use the pipe block. And the last one, we should take one sentence, which is worth remembering. Yes, thank you very much. And I think we have time for discussion.
Fritz, thank you very much. I couldn't agree more. I'm using pipe way too less. I promised to use it more. I will do so today. I agree. Not all things are pipes, though. But whenever there is a pipe, should make a habit out of it. One little quibble I would have is when you made a deep copy in order to replace elements. It's great that you're using the ID block, but that this block actually creates a deep copy is sort of like a freak side effect of introducing hyperblocks. So I would probably suggest you just make another custom block that is called deep copy, and just use ID inside, because the reason why ID actually makes a deep copy is not clear. And ID essentially doesn't mean deep copy, it just means give me the thing. So we could almost argue it's like a bug that it doesn't make a deep copy. That's kind of the only quibble.
It's not a deep copy, yes. But why should we invent another block when we have one?
Right. Because sometimes labels make things clear. See, I noticed that you're going out of your way to sort of build a bridge to text-based languages, or to the thinking of mathematics, kind of mathematical notation with by using parentheses and commas in the labels of your blocks, which you also
this is the German curriculum, so we are obliged to do this.
Oh, you're just being obedient. Okay, good.
No, we could. It's what you did a lot of those other blocks too.
Well,
it's more friendly, more user friendly.
See, but I would assume if it's in the curriculum, somebody probably has a reason to believe that it helps students understand something, and so it might help to just make a block that actually says on its label what you expect it to do,
which is not allowed in the Abitur. That's the limit for us.
No, but that was just a minor quibble.
Yes.
Other than that, I agree with almost everything. I have to say that at some point, my head started spinning about all the imperative function definitions of what then turned out to be reporters' functions. So, but maybe, as you say, I'm just too indoctrinated by Brian to use reporters for everything. I'm often finding them easier to read than trying to follow along which command mutates which other value that happens to be a deep copy and not. So I actually find that style very hard now to process in my head.
Yes. But the problem is, I totally agree. The problem is the textbooks start with commands, and not only the textbooks. Eckhart in 2022, for example. So I said, oh, he hasn't taught a course in at least 15 years. They would have taught him otherwise. And it's easier for the students too. I agree totally. But when we start thinking with reporters and making operations on lists, this is the way to functional programming. The easiest way. There is another one. I don't know it. Maybe Brian knows another one. But I think this is the easiest way for the students to get, oh, yes, this is kind of thinking. We had some, I don't have an example. We had, at some time, we had 4 reporters stuck into the first one, but and then to make it from this 4 reporters working on the same data to make this a functional program was very easy. Just put them after.
And I really think this opens up a whole very important dimension to your work, and something that we need to discuss more. Because what you're kind of the brilliance of your work is kind of what Brian said in his talk, kind of being subversive by sort of catering to the curriculum and to the and using these things, and then sneaking in more powerful ideas, but doing it in a way that isn't immediately noticeable, and that so I get it. So you can't be radical and do it all reporters all the way down. Kind of you need to follow the traditional style, and I think that's the danger is that you're being criticized by everybody, like you're being criticized by those who want to do it, imperatively and use OOP, and at the same time you're being criticized, like for people like me, for not being too functional. Okay, I get it. But that's the hallmark of somebody who tries to innovate education.
The students come back to me after 2 years when they left school, and they said, "We didn't believe this was a real programming language. We ever thought real programming would be done in text space. But now we compare us with the other students, and we think we have learned programming, and they have not. They only learned the beginnings, and we have learned much more. So, but we did when you taught us this, we didn't believe you."
Yeah, I get that all the time.
You want?
Yeah, sure. I think I'm pretty optimistic about what students will or won't find easy or hard. So, I mean, you started out by talking about, we old people learn old ways. And that affects the code that we write. But I think it also affects the assumptions we make about students. Once you know what map means, everything becomes so much easier. I mean, yes, you have to learn it, but it's no harder than learning that you were talking about zero origin indexing. That's a kludge. Well, but students aren't going to find that easy, because with zero origin indexing, the ordinal numbers don't line up with the cardinal numbers, right? So the 23rd element of the list, now, is that item number 23? No, I know it's not item number 23. Is it 22 or is it 24? That's hard. I think that's much harder than map. So just, dive in is my, and about pipe. Yes, you're absolutely right. I think unwinding the composition of higher order functions is easier for students to learn. I would want students who leave my course to be able to do it the nested way.
Yeah.
But yeah, if I were writing a curriculum today, I would use pipe much more than I have done in the past.
We saw the reaction from the pupils. Before we went to change to B by OB, when we're using Delphi, we had our first course on advanced level was, I think, about 11 points in the non-coding tasks and 4 points in the coding tasks. And it was a real gap. And Kerstin get almost the same, a little bit smaller, but also the same gap between coding and non-coding in her courses too. So she made it the same. And then when we changed to V by OB and Snap, this gap closed relatively very fast. The first course was not, they changed to Snap in autumn 2011, but the second already had closed this gap. And so they did much better coding than with the traditional way. And this kept during the whole time. The stayed through the whole time.
When you presented this, was very interesting that we are still in this imperative programming world, and that even such a step to higher order functions seems to be a huge task still at universities. And I was wondering, or I was starting to think, what actually happened to the way that even the programming language has a built-in way to recursive findings like Prolog. Do you teach that in school? Because I think that is something that would be a wonderful flavor if you have the deep first search inside, and then you could have quicksort is in the internet in 4 lines with Prolog, for example. So you could even dense this. And that is something that I've seen in JavaScript already, that they tried it with yield Prolog or tau Prolog as a flavor on JavaScript, that you build in the DFS. Is that something that you teach at the university? Because that
I think you must estimate the question in German. I didn't get it in English.
If you use Tiefensuche,
yes,
then you could condense the code for these quicksort algorithms to 4 lines, because then the recursion, you only test if the pivot element is smaller, and then you call again the quicksort. So the code is much more condensed.
I must look this up. We haven't had Tiefensuche DeepSeek in the last 10 years. I don't know when we had the last time. So we had it in the curriculum, but at that time we had a curriculum which was written every year and was valid only for one course. And there was, must have looked it, should have looked it up. I don't know it. I can't remember how we did it. I don't think we did it with higher order functions at that time.
Mm.
It was, I don't think if we didn't have higher order functions. When came the higher order functions? Yes, but at when?
In version 3.
In version 3. So at that time we didn't do Tiefensuche in the course. We just have to give it a try. Maybe I look it up and try it.
So my question is, when you start with them for these algorithms, of course, some are a little you would not sort when you would do it on your own, on a paper. Some things you would do different, But do you also animate it at the beginning a little bit for the students to understand? As a step, you can have graphics or a little bit animation, that some things are a little bit clearer, also how the data is changing. But of course, I'm not sure when you go to the higher order functions, if you can do this still then, because then maybe too much is done in one step.
Yes. Yeah, but so we use these little, I call them building blocks. Higher order function for a specific purpose, for filtering, for example, to get rid of maybe all the odds or so elements of a list. And then we have this paper or this electronic paper, and you can use you have a problem and can say, oh, somebody solved it that way. And then we collect. The next one comes and says, oh, I just discovered we can use higher order functions in this way. And we take it into the library. And then when this started, then the not so advanced students say, we stay with for loops and so on, and we use 1 or 2 or 3 of these building blocks because they are very, very good for us, and they make our work easier. And then the more advanced students say, oh, this is a very different way to think about computing. And they took the old programs, for example, Playfair. We did Playfair, the classic style. And then 1 year later, we switched to using more and more higher order functions. And they said, oh, this would be done in higher order functions too. And they started to rewrite their own solutions. So we have at least 3 solutions: classical imperative solution, the more reporter-based solution, and then the third one was when they went to, but not every student did it in the same way. And so I had, for me, it was very comfortable, but I could differentiate my lessons without much additional work. Could set a task, and they could solve it with traditional things. They could solve it with some building blocks of higher order functions, or they could do it in the functional programming.
But when they start with for loops, but you do not animate it in a way, so to say, just for a visual, that you see, for example, when they change the position in the order, for example, and then you change the position again. And if you would have it animated with some objects or sizes, then of course you would directly see also sometimes this shift and this moving to the back.
We use the visual data in recursion. I remember when I had to learn recursion, we did it with Towers of Hanoi, but without graphical representation. And I just didn't get it. And then when we do graphic recursion, as in Julian-Dwarf computing and others, you can see it. So I just start everything by way of graphic. You must see it. Not just understand it. Then we can take, so how does it work? And then we can use the code. And the deep understanding of recursion comes only over the time, not the first time you are using it. You're using it as a receipt so that we can solve certain problems with this easier than with imperative programming. But it's slowly it grows. This means recursion. And on the start, when we do recursion, we must have a base case, and we must have recursive 1 or 2 recursive calls. Okay. But that's enough.
Yeah. Thank you.
But I think it's a good idea to do some graphics, maybe with the plain text on the crypto text, the circle that you showed, so that everybody can easily by the graphics understand what is happening, and you see them.
Actually, graphics was what we did. Start. We did a lot of simulations such as this one. What is insertion sort, what is bubble sort, what is merge sort. And so we tried to give graphics. And it was easy in Snap. To do this in Delphi, it would have been possible. But what would it require? So I could give it to the more advanced students. Said, so we have this sorting algorithm. I had one group, two girls, and it just came to the one was working on the task at hand, and the other was drawing. So I said, oh, we always do this. The one is looking for the solution, and the other is make it more beautiful. So, both are computer scientists, though.
A few words about quicksort. The sort of abstract idea of quicksort, which is a partition sort, technically, is really easy to do using filter twice to get the small numbers and the big numbers. Quicksort, what makes it quick is the very low level of abstraction at which it was designed. So it crucially depends on the fact that those numbers are in a consecutive array in memory, and it has the 2 pointers going up and down, and so a faithful rendition of quicksort is necessarily hideous. So I have stopped talking about quicksort, and I just talk about partition sort. And I say, by the way, quicksort, which is what everybody uses, is a kind of super hacky optimized partition sort. And that makes me feel less like I'm telling lies to the students. But I don't understand why everybody doesn't use merge sort, actually, because merge sort is so beautiful and so easy. Anyway, there you are.
We took years to only use merge sort. And then one came up with this solution and said, oh, boom. But never use it. We use the merge sort every step, because it's easy to make the complexity and so on. To add another layer, to double the elements, you get another layer. And so it's very easy. It's very complex. We couldn't teach complexity of quicksort in school. They do it in university, but I looked the proof up, but didn't get enough mathematics.
I was quite taken by your looking at the finite state automata, which I think make a very nice example of when two different representations of a problem, the diagrammatic one and the tabular one, lead to very different solutions. And I think one of the interesting things about programming, which we don't often address, is how do you think about the problem in the right concrete way as opposed to the abstract way, so that your solution makes sense to you while you construct it. And that's a lovely example of when you get two totally different approaches. And I have no idea how to approach the problem in general, but I think it's an important one for programming.
Yeah. That's where the students come, or the pupils come into play, because they see those abstractions when you don't see them. At least this was my experience.